This is the only satisfying video on explaining the open delta configuration of a source and a load on YouTube. Firstly, remember your unit circle. It's called unit circle because it has a radius of unity. Unity is a pretentious way to say 1. Now, why is a unit circle helpful? Well, remember with your trig functions, if you cast SOHCAHTOA as a spell, it's a fancy mnemonic to remember that your sine of your angle is your opposite leg over your hypotenuse. Cosine is adjacent over hypotenuse. Tangent is your opposite over hypotenuse. Opposite over adjacent, rather. So sine of 30 would be equal to your opposite over 1. Well, we already know that for the unit circle, the y-coordinate is 1/2 at an angle of 30. So your sine of 30 is 1/2. Your cosine of 30 is √3/2. These are some other values. Cosine of 60 is 1/2. That's another thing just to memorize. Okay, I'll breeze by that. If you're probably confused if you don't remember that, but that's important for vector addition. Now, positive sequence voltage phasors. Quite a jump from high school math. But if you picture you're standing right here, as these phases spin in time, you'll get slapped in the head, A, B, C, in that order. That's why it's positive sequence. I guess I could mess this up and draw some waveforms. I'm holding my phone in one hand, so this is rough, but over time, of course, these would be kind of overlapping more, but these would be your phases, A, B, C. C happens after A. So if you imagine they're all traveling this way, at some point in time, you'll have the A peak, then the B peak will come by, and then the C peak will come by. Anyway, often you'll need to add voltages or subtract voltages. Quick primer on that. If you want to find VAB for a line-to-line voltage based on two line-to-neutral voltages, VA and VB, VAB is the same thing as VA minus VB, or VA plus the opposite of VB. So if we have VA on the unit circle, so it has a magnitude of unity, VA plus minus VB plus the opposite of VB, well, if you take your x and y coordinates, this is 1, 0, we already know something on the unit circle at an angle of 60 is 1/2, comma, √3/2 for the y. So the sum of those, your new phasor would be at an x coordinate of 1.5 and a y coordinate of √3/2. You can find the magnitude, it's square root of 3. What's the angle? Well, you can find that out with your trigonometry. Tangent of theta is the opposite, which is √3/2 over the adjacent, which is 1.5. 30 degrees. You could do it with a calculator, but this is pretty quick. Anyway, that's enough of that. Let's get into the real meat. You have a delta source in this case. It is important that it is a source and not a delta connected load. Usually the things I see on the internet don't distinguish when they talk about the open delta. So let's draw some phasors first. There's a whole lot of stuff going on. If we have our delta source drawn this way, A, B, C, sources always have the current flowing from minus to positive for your voltages. Loads, you would define the current flowing in. It will help you out. Okay. We have VAB, VBC, VCA. Those are our positive sequence voltages. I'll get to how it's different from this because VA instead of VAB, etc. Now, let's define a line to neutral voltage of a magnitude of 1. So we already know from before VAB will be the square root of 3 at an angle of 30. And you can do the math on your own to arrive at this, where VBC or VB minus VC or VB plus the opposite of VC coming here, you'll get this. square root of 3 at an angle of minus 90. So look at all these. We have VAB, VCA, VBC, VABC. Okay, soak that all in. Now, what is our current magnitudes? Well, let's assume, I think it's easy rather than working with a bunch of letters and numbers, just to assign a value. So let's just assume the source here has a resistance, pure resistance of 1 ohm. That will not be the case, but it's instructive just to get some things down on paper here. Your current magnitude will be Ohm's law, V over Z. V equals IR, so I is V over R or V over Z. What's VAB? We already know it's magnitude of root 3. What's Z? We just said we're just going to say it's 1 ohm. Okay, our current in this phase is a magnitude of root 3. Phase current refers in the delta to the current flowing through here. Line current always refers to something like a transmission line way away from here. Okay, what's our power? Well, there's a few ways to take the power. We can do a cheaty way here because we've just defined our current and voltage in phase, which is usually never the case for these. But one easy way is 3 times the power through each of these resistors, which is 9 watts total, or 9 VAs. Okay, the IAB is in phase with the VAB since we have our impedance of 1 ohm. So let's draw some currents. Whoa, how did we get here? Okay, let's look at KCL. We have the following: currents entering a node equal to currents leaving a node. So if we take IAB entering a node A, that is equal to the sum of IA leaving the node and ICA leaving the node. Well, IA is also IAB minus ICA, and IA is equal to IAB plus the opposite of ICA if we just rearrange it. So how did we get to IA is 3 amps? Well, you already know IAB is in phase with VAB because we've defined our impedance here to be purely resistive. So VAB is at an angle of 30. IAB, we don't know the magnitude yet, but we know it's at an angle of 30. We know ICA will be 120 from there if we're doing positive sequence. So the opposite of ICA will be at minus 30. Well, let's see here. It's a square root of 3 magnitude for IAB because we just solved it with here. Now the magnitude of IA, we just do our same vector addition as before, but this time it looks like this. So for delta, the line currents are actually larger than the phase currents. Very interesting. Now that we have all that out of the way, how does this inform us for the open delta? Well, the open delta was very troubling for me because no one really explains these constraints. Usually you hear that the open delta has some weird ratio of the power it used to provide, but they don't explain these. So these are the true constraints I was aware of after a lot of research. The generator can still only produce whatever phase current it was producing before, meaning we were operating with all of these windings fully loaded. So if that doesn't make any sense, think about you have a motor. The motor can only handle a certain number of amps through each winding. If you lose a phase in this case and you want to increase to have the same power, you can't go over the current rating of your phases as before. So basically you're locked into the magnitude of your phase current as 0.3 or root 3 amps in this case. Also, your phase voltages are unchanged. It's actually interesting if you take a KVL loop and you sum all these and equate them to 0, VBC is actually the same as before, even though there's no phase. It's here. Okay, now for the big one. This one was the bane of my existence for like a whole day. Line current angles are unchanged. So that seems bizarre. Why is that a constraint? Well, imagine this generator is part of thousands, tens of thousands of other generators in the electrical grid. Well, just because this one generator loses a phase, it's not going to change the current angles for the entire grid. So we're assuming a stiff source, which usually just means infinite bus, a million generators, or your source impedance is way less than the load impedance. So that violates V equals IR for your source resistance here. So you can't just start to say, oh, well, the current's the same, the angle's the same. No, you have to kind of ignore that. This is kind of a weird thing about open delta that people don't usually explain. So let's move on. How do we find the power? We know before we had 9 VAs or 9 watts. What can this guy produce if it's hooked up to the grid and it loses a phase? Well, let's see. We just said that the magnitude of the phase current is unchanged at square root of 3 amps. Okay. Now the phase angle of IAB, well, clearly that just has to be the opposite of the line current angle IB. If this is fixed, there's only 2 currents in this node. So IAB is equal and opposite to IB. Now, IB, we just said, is at an angle of minus 120 because it's the same as before. So plus 180 is 60 degrees. So what do we have here? IAB is square root of 3, magnitude, angle of 60. That also means IB is the same as before with its angle, but its magnitude that this generator is delivering is smaller than before. Its magnitude is square root of 3. Okay. You can pause the video and prove to yourself that IC is a square root of 3 at an angle of 120. Same thing, IC, ICA, 2 currents. This time they're equal to each other because of how we drew the directions. That's why we have them right here. Now, the interesting node, IAB here, IAB entering this node A, is the sum of IA and ICA, KCL. Use the point here. IAB is the sum of these 2 currents. Okay, well, let's rearrange. So for IA, it's IAB plus the opposite of ICA. We already know IAB is here. We already know ICA is here, opposite here. Oh, we have 60-degree angles. We know the cosine of that is going to be 1/2. So even though we're doing vector addition, usually we're used to the square root of 3 being the resultant magnitude, but that's when we're adding things 30 degrees apart. If we're adding things, 60 here and 60 here, well, it's going to be the same magnitude. So IA is square root of 3 at an angle of 0. So here are your line currents, IA, IB, IC, and here are your phase currents, ICA, IAB. There's no IBC because there's nothing there. What about the power? Well, we can take the complex 3-phase power. We said before it was 9 volt amps. This is another equation you can use to find 3-phase power. Square root of 3 times the line-to-line voltage times the line currents. Before, our line-to-line voltage was square root of 3 and our line current was 3 amps. What do we have now? Line-to-line voltage is the same as before, square root of 3. Our line current is not 3 amps anymore. We just said it's limited by the generator, so it's a square root of 3. So our total volt amps is 3 times square root of 3. If we take a ratio of the old power to the new power, it's this. Multiply by here, make it look prettier. Square root of 3. There's square root of 3 less power now, square root of 3 more power before. That comes out to about 58% of before. Now, if this were a load instead of a generator, then it would have 2/3 of the power consumption as before, because you're not limited in your current here like you are in a generator. Now, if it's a load, you can take Ohm's law and say V equals IZ and solve for your power consumption here. Let me know if I missed something.